Hello everyone, welcome back. We were in the process of deriving relationships between variables across the normal shock for varying Mach numbers for the incoming flow. That is what we were doing. In that we had a point where we had to decide which shock will actually happen, either expansion shock or compression shock, and we went through entropy arguments and we showed that I will go and draw that plot here again. We had a plot that was looking like this, that is, for Mach number less than 1 we were having delta S by R that was slightly negative or more negative depending on very low Mach numbers. For very high Mach numbers more than 1 we are going to have delta S positive, and we said that because of this reason we are going to say only M1 greater than 1 going to M2 less than 1, that is the only solution that is possible, which corresponds to my gas gets compressed across the shock. So, we are talking it is only compression shock is possible, that is what we said. And I also was very careful in telling you the statement that was when we say only compression shock is possible, I also included this thing saying it is for our air. Okay. If I want to think about, I am currently going beyond the course curriculum, I am just telling you, if you are interested you can go read up more. If we are in a gas which does not obey P equal to rho RT, this is what we have been using all this time. We said P equal to rho RT for us, our gas, and so we got this behavior. Okay. If there is a gas where this is not true, say if I take the van der Waals equation, which is also known to people already, so I am using that. An equation of this form where A and B are two constants for that particular gas for that range of pressures and temperatures which we are interested in. This is going to be the equation for such gases, where if I say A and B are 0, it becomes P equal to rho RT. Okay. If there is a gas that is obeying this, then we can call it either the van der Waals gas or they gave a better name for it, as in people who studied this, based on them they get a name, it is called the BZT gas. BZT flows is what they call for flows with this kind of gas. It is for 3 different people, the names are Bethe, Zeldovich, I think there is an apostrophe somewhere, yeah. And the third guy is Thompson. I will write Thompson here. These people worked in the 1940s and he worked in 1970, 60s and 70, and they studied flows where expansion shocks are probably possible. Okay. The way it works is like this. I will go to a plot here of our state diagram. I am going to use P and V, and for our common gas it is going to look like this for T equal to constant line. But if my pressures and temperatures are very low, where van der Waals forces are important, or my gas is such that it is important, the curve may look like this. If you are very close to, say, condensation of water vapor kind of ranges, things may change and do crazy things like this. Okay. am not sure whether air with this little percentage of water vapor will it affect, I do not think it affects, okay. But I may get such a curve for special gases. Typically the refrigerants which people use will have such characteristics. Anyways, in this range the gas may behave differently, because this is the opposite slope of dP by d rho I will get here compared to all the other places. This behavior is similar to this behavior is similar to this behavior, but in this small zone alone, if my temperature, pressure and volume or pressure and temperature are such that my gas is operating in this range, then I may have expansion shocks and only compression waves are spreading away from each other. That is also possible. Okay. This of course is not in the scope of this particular course. I am just telling you there are things that are out there which we do not deal with in our course. That is the only thing I will say about this, and then we will not talk about BZT flows anymore. It is there somewhere where there are some gases where we can have expansion shocks and compression fans. Of course, you do not know what they are right now, so I should not be talking about it more. Now, we will go back and derive every ratio variable which you have been deriving all this time in terms of M1 and M2 in just terms of M1 alone, just one variable. Okay. So, we had this variable P2 by P1 which is 1 plus gamma M1 square by 1 plus gamma M2 square. I had this. Now, I will substitute the M2 square which we got last class. I wanted to write it separately, so I will put a line here and write it here. M2 square, we got it to be 2 plus gamma minus 1 M1 square divided by 2 gamma M1 square minus gamma minus 1. I had this expression. Now, I want to substitute this M2 square inside here. So, P2 by P1 will now become 1 plus gamma M1 square divided by 1 plus gamma times that expression in here 2 plus gamma minus 1 M1 square divided by 2 gamma M1 square minus gamma minus 1. Now, I want to simplify this, it will come to a very simplified expression. So, I know that already, so I am going to say I want to simplify this. So, what I will do is I will take this denominator, multiply it with this 1 and take that whole term to the numerator up there, that is all I am going to do. Then it will become 1 plus gamma M1 square times 2 gamma M1 square minus gamma minus 1 divided by this multiplied with the 1. So, that is going to be 2 gamma M1 square minus gamma minus 1 plus 2 gamma plus gamma times gamma minus 1 M1 square. This is what I am getting here. Now, we want to simplify this expression further. I had this particular form. If I look at terms in here, if I group it in a particular form, it will come out to be nice, but let us say I will go one step slower. Okay. I will just try and simplify it the way it is already. What can I simplify here? Minus gamma plus 2 gamma. I can simplify that. I am going to link these two, okay. That can cancel each other. Of course, there is a plus 1 here, nothing can be done with it currently. There is a gamma, nothing can be done. 2 gamma M1 square is there. Here there is minus gamma M1 square. So, that can be simplified a little bit. I will remove that 2 with this minus 1. I will again link these two. This is how I cancelled it. So, the remaining terms just stay. Okay. There is a gamma M1 square, there is a gamma square M1 square, and then there is a gamma, and then there is a plus 1. Those are the 4 terms that I have in the denominator. Okay. So, I will write this, continue it here. I will keep the numerator as is, that is the same numerator. Now, in the denominator I will write it in a different form. So, it will be gamma plus 1 plus gamma m 1 square plus gamma square m 1 square. This is what I have. I wrote it in a different order, that is all I have done. So, this now if I look at these two terms, this will just be gamma plus 1, there is a gamma here, there is no gamma here, that is the only way I look at it. Gamma m 1 square can be common, this is what it comes out to be. So, now I can write this whole expression as P 2 by P 1 equals I get to this particular form. Okay. So, basically I have just pulled out a 1 plus gamma common here, then remaining will be 1 plus gamma m 1 square. Now, I am just directly going to cancel these two, whatever I have left is my final answer. I can leave it like this, or I can simplify it one more step, which is what I will do. Okay. So, I am going to look at this term, this is 1 minus gamma plus 2 gamma m 1 square. Okay. I want to make it 1 plus gamma on the top, that is what I want to do. So, I will add and subtract gamma here, minus gamma will go with this already existing minus gamma here. So, it will become minus 2 gamma, and the remaining I will write it one step here, plus gamma minus gamma. I have added these two terms here now, and I am going to group this and this together. I am going to group these two together, that will give me a minus 2 gamma, and then the remaining term will be gamma plus 1. So, I will write it as 1 plus 2 gamma m 1 square minus 2 gamma divided by gamma plus 1. This is what I have, which can further be simplified as 1 plus 2 gamma by gamma plus 1 times m 1 square minus 1. That is your final result. It is extremely simple, this is equal to P 2 by P 1. I will write it here again. Okay. Very simple form, easy to remember. Now, we will do the same thing for rho 2 by rho 1, because I know this is going to give me a simple enough expression. Okay. We are going to start with what we have derived already. We have derived this long back, that is 3 classes before, I believe. It will just come out to be this form. Okay. Hopefully, you remember that we derived this long back. When we started with normal shock, we derived this, the very first class of normal shocks. Now, I want to substitute that P 2 by P 1 which we just derived in here, okay, and it will become P 2 by P 1. I do not want to write it as 1 plus 2 gamma m 1 square. So, I will write it as gamma plus 1 divided by gamma plus 1. Okay, this way I can cancel the gamma plus 1, that is why I wrote this way. Okay. And the other one will be gamma plus 1 by gamma minus 1 plus 1 plus 2 gamma by gamma plus 1 m 1 square minus 1. Here I am retaining the original form which we had P 2 by P 1 we derived just now. Okay. In the numerator I have multiplied this gamma plus 1 in there and put a common denominator gamma plus 1. That is what I have. I can cancel this gamma plus 1 directly there. So, I am going to have a slightly different expression. which I have to rearrange eventually. So, I will start pulling out gamma plus 1 by gamma minus 1, okay, that is one term, plus 2 gamma m 1 square by gamma minus 1 minus 2 gamma by gamma minus 1 and then plus 1 is there, I will just keep it like that currently, divided by, now I have to rearrange this whole group of terms. So, I will write it as currently gamma plus 1 by gamma minus 1 remains the same, plus I will pull out this minus 1 with 2 gamma by gamma plus 1 along with this 1. So, it will become 1 plus gamma minus 2 gamma divided by gamma plus 1 plus 2 gamma m 1 square by gamma plus 1. It is all just algebra, I am just rewriting things in one way or the other. Now, I have to simplify this. I will look at the numerator terms first. I will keep the m 1 square term separately, I will link all the other terms together. So, that is going to have a common denominator gamma minus 1, numerator is gamma plus 1 for the first set, and then I will take this minus 2 gamma, and then this 1 can be written as gamma minus 1 by gamma minus 1. So, it will be gamma minus 1. Okay. This is all I am having. Now, if I look at it, I will write the remaining one term also, then I will start cancelling things, 2 gamma m 1 square by gamma minus 1. Denominator will come and write later, but as of now numerator everything goes away, this whole term goes away, only this term remains, that is a nice thing about it. Now, we will go to the denominator, I will write it one more step like this, gamma plus 1 by gamma minus 1 plus I will simplify this, this will become 1 minus gamma by gamma plus 1 plus 2 gamma m 1 square by gamma plus 1. This is what I have now. Now, I have to simplify this set of terms. If I make this multiply these two together, it is going to have gamma square minus 1 as denominator and numerator will be gamma plus 1 square plus, oh wait, I am having 1 minus gamma and gamma minus 1. Okay. So, I am going to have a minus sign of gamma minus 1 square. This is what I will get. I can write this as minus of gamma minus 1 and then gamma minus 1 multiplying gamma minus 1, I am getting gamma minus 1 square. I am just looking at this one term right now in the denominator, I will write the whole thing later. As of now, I will just look at this term, that is coming out to be this, okay, just this one term is this, which now if you look at it, it is going to be a square plus b square minus 2 ab, and you will find that a square and b square will get cancelled with this a square and b square, only thing remaining will be this will have a plus 2 gamma minus 2 gamma, that will give you 4 gamma total, 4 gamma by gamma square minus 1. This is what I will have for just this set of terms, remaining term exists still. I will write this whole thing in the next corner again. We already found that the numerator is very simple, 2 gamma m 1 square by gamma minus 1. Now, we have simplified the denominator and it looks like 4 gamma by gamma square minus 1 plus 2 gamma m 1 square by gamma plus 1. This is what I have. Now, I will take this gamma minus 1 to the denominator and multiply it throughout, that is the next step. Okay. If I do that, when I multiply that gamma minus 1 with this term, gamma minus 1 into gamma plus 1 is what gave this. So, it will become gamma plus 1 in the denominator here, we will write it one by one. So, it is going to be 2 gamma m 1 square divided by 4 gamma by gamma plus 1 plus 2 gamma into gamma minus 1 m1 square by gamma plus 1. This is what I have. Now, I can take this common denominator gamma plus 1 and put it up there. So, I will rewrite it as 2 gamma into gamma plus 1 m1 square divided by, I am having 4 gamma plus actually I will just take out the 2 gamma first, so that I can cancel it with the numerator. 2 gamma into 2 plus gamma minus 1 m1 square, we will write it like this. This is what I have. If I write it up to this point, now I can cancel this 2 gamma with this 2 gamma, and I do not think I can simplify this anymore. So, that is my final expression. I will write rho 2 by rho 1 is equal to gamma plus 1 m1 square divided by 2 plus gamma minus 1 m1 square. It so happens that this is also equal to u1 by u2. Why? From mass equation. Okay. So, this is another set of relations we have. Given the m1, I can find the rho 2 by rho 1, I can find u1 by u2. I already wrote an expression some time back for the third board, p2 by p1 in terms of m1 square, that is also given. So, the next thing left is t2 by t1. I tried deriving t2 by t1 in any simple form, but it is very complex. So, we will just keep the simplest form. M1 square on the numerator. And this is the only form I will keep. Where is this coming from? I am going to say T naught 2 equal to T naught 1, and I am using energy equation. Basically, T naught 2 by T naught T2, T naught 2 by T2 is 1 plus gamma minus 1 by 2 m2 square. Similarly, T naught 1 by T1 will be 1 plus gamma minus 1 by 2 m1 square, and I have just rearranged the 2 such that it looks like this. This is another expression. So, now after this whole set of expressions, I just want to have in your notebook one page which will have all the formulae together for normal shocks, like we did for isentropic relations. We want to have one page just all the possible relations for normal shocks. So, first thing I can directly say T naught 2 equal to T naught 1. We proved this long back, we will just keep it that way. Next main thing, I will divide the board somewhere here, because I want to write some parallel set of relations there. M2 square, we derived this towards the end of last class, and we used this extensively today. 2 gamma m1 square minus gamma minus 1, that is the next relation, and then we just derived a whole set of relations. I will write the whole set of them here, p2 by p1. One nice form for p2 by p1 is 1 plus gamma m1 square by 1 plus gamma m2 square. This is a nice form, so I will always want to keep track of this. Another form which we derived today is this. Okay. Now, this can also be rearranged in one more form, which we actually did today. During one of the derivations, it came out to be this. I am writing this also because this numerator is shared by this thing as a denominator. That is the only reason why I will keep this. This denominator is same as this numerator. That is the only reason I will like this form also. In case sometimes I have m2 square multiplying p2 by p1 in any relation, I may need to use this kind of form, that is all. Ideally you can use any form, it will automatically rearrange itself, that is the beauty of math. Anyways, now the next thing is rho 2 by rho 1, we know that it is equal to u 1 by u 2, which we just now derived. So, I will anyway write the expression here for completeness sake, gamma plus 1 m 1 square divided by 2 plus gamma minus 1 m 1 square. And we said that there is no special relation for T 2 by T 1, I will write that expression also here. These are the set of relations we have. One more I have not written here, I will come back to it, but before that I will also write the other set of parallel relations, one ratio in terms of other. It is supposed to be rho 2 by rho 1. That is one relation, rho 2 by rho 1 in terms of P 2 by P 1. Of course, it can be obtained by rearranging the top one. Of course, this is equal to u 1 by u 2. T 2 by T 1 in terms of P 2 by P 1 can be written in a different form. I do not think I derived this particular relation, but it is not very difficult to get. If I take this rho 2 by rho 1 and then I take this P 2 by P 1, I am going to say T 2 is P 2 by rho 2, T 1 is P 1 by rho 1. So, if I use this divided by this, actually no, I do not need to do that, I want everything in terms of P 2 by P 1. So, I am going to take this, multiply this with P 1 by P 2, that will give me I want the reciprocal of this multiplied by P 2 by P 1, that will give you this relation. You can go write it, it is not very difficult, I will just write that expression here, P 2 by P 1 times rho 1 by rho 2. I am using this rho 1 by rho 2 from here, reciprocal of this multiplied by P 2 by P 1, then I will get to this form. This is another form which you can get. Now, other than this, I want to write one more expression here. We have not yet derived it, but for completeness sake I will put it here and then I will derive it now. Okay. One simple thing is P 02 by P 01. Okay. This is not very difficult to derive, I will just write it here. We use a particular technique which is very common in gas dynamics. We have expanded this particular ratio into a product of 3 ratios. This is a cyclic product of ratios, that is what you have done. Okay. If you look at it, I have expression for this in terms of 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1, similar expression for this, just the reciprocal of that, and then P 2 by P 1 we have a relation here up already. So, I can get this P 02 by P 01 already. Okay. Of course, I can write that expression, but you know the expression, I do not need to write it separately. One more remaining expression which belongs in this column I will write here is delta S by R, the entropy change is equal to log of P 01 by P 02, where this delta S is actually S2 minus S1. It is actually S2 minus S1 is coming out to be log of P 01 by P 02. Now, this is the only thing which I have not derived, we will derive it now. Not very difficult to derive, it is easy enough. I just have to start with the second class of our thermodynamics review, delta S is Cp log T2 by T1 minus R log P2 by P1. We had this form already, and we are going to say calorically perfect gas kind of assumptions. This Cp can be written as gamma R by gamma minus 1. Once I have this, I can pull out an R and put it below delta S. So, I will rewrite it as delta S by R equal to log of gamma by gamma minus 1 is in front of log. I can take it inside the log by putting power of T2 by T1. So, I will make it T2 by T1 to the power gamma by gamma minus 1 minus another log is there. So, it will become reciprocal of P2 by P1, so it will be P1 by P2. I have made it into one log, that is all I have done. Now, I have expressions for T2 by T1 and P1 by P2. We just have to put the appropriate expressions, and it will be comfortable enough. And if you use the wrong expression, I will get a very complicated relation. You have to use the correct one so that it looks simple enough. Right. So, I want to make everything in terms of stagnation pressures and stagnation temperatures, because I know something about the stagnation temperatures, they are equal. So, I will write this T2 by T1 as I will write it as T01 by T1 divided by T02 by T2 multiplied by T02 by T01. This is correct. Okay. Now, what I want to do is I will write an expression for this in terms of M1, I will write a function expression for this in terms of M2, that will come out to be, and I know that this is equal to 1, okay, T02 equal to T01 across a normal shock. So, I can just use this. Now, I will go look at the remaining terms alone, that will be 1 plus gamma minus 1 by 2 M1 square divided by 1 plus gamma minus 1 by 2 M2 square. I have this. Now, I have to look at P1 by P2. This can be written in terms of stagnation pressures again, that is going to become P02 by P2 divided by P01 by P1 multiplied by P01 by P02. I will write it like this. Currently, we will keep it like this, P01 by P02, we know that it is not equal to 1, it is something other than 1, we will keep it, but the other two expressions I can write in terms of 1 plus gamma minus 1 by 2 M square, P01 by P02 times 1 plus gamma minus 1 by 2 M2 square to the power gamma by gamma minus 1 divided by 1 plus gamma minus 1 by 2 M1 square again to the power gamma by gamma minus 1. Now, if I go back to my delta S by R expression, I have a T2 by T1 to the power gamma by gamma minus 1, that is T2 by T1 to the power gamma by gamma minus 1 will be this to the power gamma by gamma minus 1, while this is P1 by P2 expression is here, which is also having almost this to the power gamma by gamma minus 1. If I look at carefully, M2 square is in the denominator, here in the numerator, when I multiply these two they will get cancelled. Similarly, M1 square will get cancelled with this one. So, finally, I will be left with just P01 by P02. So, that is how I am deriving this. Delta S by R will finally just come down to log of P01 by P02. Okay. This is S2 minus S1 is P01 by P02, that is what you will get. Okay. And of course, you should know from here that P02 is always less than P01, because we want entropy to be increasing. Delta S has to be positive, which means this log has to be positive, which will happen only if the ratio is more than 1. So, I can tell that P02 is less than P01 directly. Okay. So, this is the derivation for the previous page I gave you a formula sheet. Now, we have come to a point where we have to get more physical feel for stuff. So, we will go and plot thermodynamic process. I am going to look for thermodynamic process here. I am looking at TS diagram. TS diagram. So, first thing I will mark will be at T0 because I know it is a constant. Now, I will mark a P01. This is T0, T01 or T02 both are equal, I just put T0. Now, I will mark a P01, that will be some curve. You know that constant pressure curves on TS diagram will be exponential curves. So, it is going like this, I will put it as P01, that is pressure equal to P01 will be this curve. Now, I am telling that for this T0, T star is here, and I am saying my flow incoming is supersonic, which means my P1 T1 will be somewhere lower. This is my T1 line, and I know this is the stagnation condition, which means this is the entropy value. So, my P1 must pass through this point, that will be another exponential curve going like this. This is my P1 curve. So, my actual state on this diagram is P1 T1, which will be this point, that is my initial point, that is where I am. From here I am going to a subsonic line, that is I am crossing this line and going above. So, let us say this is my T2. I am crossing my T star and going to some higher temperature. As I am doing that, I am also increasing entropy. So, I will put an entropy line here. So, this will be my new state, and so I am going to put a P2 line through that, curve through that actually. This is my P2 curve. So, this is my actual state T2 S2. I will call this S1, this is S2, T2 S2 will define my state, right, two thermodynamic variables, or I could use T2 P2, that will define my state. Anyways, so I am having these two, this is my state 1 and this is my state 2. One more thing missing is P02, it is just extending it through an imaginary isentropic process from 2 to 02, that will reach there. So, I will draw another curve here, that is my P02. It is already seen directly that my pressure drops, P02 should be less than P01, graphically also you can see that. Now, my actual process of shock is this line, I will draw a double line so that I will tell that this is my shock. This is the actual process for the shock. When I say process, I do not know what is the exact path it is taking. All I know is it starts with 1 and ends with 2. I have drawn a curve like this, maybe somebody else will draw a curve like this. I do not want to disturb this picture, I will just take another 1 and 2. I have drawn a curve like this, maybe somebody else will draw a curve like this. Both are valid in my opinion, okay, because we know only starting point and ending point, I do not know how it goes through this currently, okay. Both are equivalent in my opinion. So, what we can say is from here the gas jumps from this state to this state within a thin layer, and we do not have details of what is it doing inside the thin layer, okay. All we know is it is jumping from here to there. So, ideally we should not be worrying about what is the path it takes, there is no path inside the shock, it is a very thin layer. So, that is the detail I have here. Now, we will go for PV diagram. Of course, every time I draw a TS diagram, I will immediately go to PV diagram, you have to get used to this. You should be able to handle the problem in both the coordinate systems. Okay. Now, here I have to draw first a constant temperature line, my T0 line, which will be a hyperbola. So, it is going to look something like this, T0 equal to constant, that is the T0 line. Now, I have to say this is my P01, I will pick a P01. Wherever this line goes and meets my T01, that is my stagnation 1 condition, 0 1 condition will be T01 and P01, wherever that meets, that is my stagnation condition. Now from there I have to go to different temperatures. What did we do here? We went to T star. So I will draw a T star curve which will be a lesser temperature than that, it will be another hyperbola. This is my T star line. Actually what I want is T1 line, it should be below this, that is all I want. So I will draw a T1 line. Okay. Once I have drawn a T1 line, oh I need to extend it further, I will extend this T1 curve all the way up to that. This is my T1 curve. Okay. I know the stagnation condition, I have to go to the static condition. How should I go? I have to go along isentropic curve. So I will draw isentropic curve through this point, stagnation condition, which will be having a more steeper curve. That is what is interesting, right. It will be a curve like this. Of course it will never cross 0, it is going to turn and go become something like that. Okay. Now so this is my state 1, and if I draw a line along this, that is my P1, that is my P1 line. Okay. And of course if I want density 1, it will be reciprocal of this particular V1, that is all. Now I have this is my state 1, and I am saying it is having the same T naught, but is going to have a lower P naught after it crosses. So I will mark a P naught 2, and same T naught and P naught 2 will mean this is the new stagnation condition, P naught 2 T naught 2, that is this point. Now I know my final state T2 must be sitting somewhere along this isentropic line. This is my S1, this is my S2 line, I have to draw a S2 line. It will be a line like this. Now I have to tell my solution is somewhere between T naught and T star. Okay. So let us pick this line as my T2. I have drawn it wrong, it should be in between these other two curves. So it will be more steep, something like this, that is my T2 curve. So I am getting a P2 line. I am just checking whether I have drawn the curves correctly, it is close enough to say that it is okay. Okay. I have to make sure that it is compression, right. I should not pick a crazy delta P that it will look like expansion, that is all. Okay. So currently I have made sure that it is close. Okay. This is my state 1 and V2 is less than V1, which says I am going through a compression process, everything is matching. So now my state, the process is something from 1 to 2, again I will draw a double line because there are so many curves. This is my jump across the shock, it is going from this point 1 to this point 2. We do not know how it goes, all we know is this is the starting point, this is the ending point, intermediate path we do not know, we will leave it like that for now. Okay. So at any time you should know that in a PV diagram my curve is going to go up and to the left for a shock, and in a TS diagram it is going to go up and to the right. Okay. It is easy to tell, shock heats the gas and it also increases entropy, that will tell you it is going up and to the right. In a PV diagram it is going to compress the gas and increase pressure, volume decreases, pressure increases, it is going to go to the left, okay, left and top, easy way to think about this. Okay. Now we want to do some analysis with the expressions we got today. Okay. So maybe there is just enough time to show some plots, so I will show you the plots, then we will do the analysis next time. So I will go to these plots in here. What I am showing you here is P2 by P1 and T2 by T1 on the same axis. Okay. While the solid lines are given by P2 by P1, this 3 lines here, the yellow is not very clear, this line, that is your T2 by T1 for one of the gamma values, I believe this is having highest compression, I am not able to see the color, I think this is yellow, is that right? So that is 1.67, okay. Gamma equal to 1.67, T2 by T1 curve looks like this. I have drawn this for 3 different gamma values, okay, gamma equal to 1.3, 1.4 and 1.67, that is what it is coming out to be, and similarly here 1.3, 1.4, 1.67, that is what I am having here. What we are seeing, first observation should be that as my Mach number increases, I have drawn from 1 to 10, as my Mach number increases, both my ratios increase, that is if my shock strength is higher, I am going to have higher and higher pressure ratio or temperature ratio. Next detail, I can say that pressure ratio is much higher than temperature ratio, and that is the next observation. If I have drawn a density ratio on the same plot, it will go in between these two sets of curves, okay, but I have not drawn it, it will look more confusing, so I did not draw it there. We will look at rho 2 by rho 1, but I will look at it later, okay. So if I have drawn it, that will go somewhere in between these two, and actually you know that rho 2 by rho 1 times T2 by T1 is your P2 by P1, right. So when I multiply this curve and some other curve here, it will give me this curve, that is what it should be. I have not drawn the rho 2 by rho 1 curve in the middle here, that is all I have done. If I look at the effect of gamma value, when my gamma value is low for the same r and t, my speed of sound will be lesser. What does that mean? If my speed of sound is lesser, my gas is very compressible, okay, and if not, my gas is less compressible. What we are finding is, for a given Mach number, if my gas is less compressible, I am having better compression, that is the pressure increases more, if not, pressure increases less, that is what we are seeing actually, okay. This is for this particular case. Temperature also does exactly the same thing. As I become more and more compressible, the gas gets compressed less, okay. I can give you reason for this, but I do not think it is useful in this particular course. It is something to do with the internal energy. Gas will rearrange that compression, that is the pressure energy, in other internal energy modes, that is what is happening inside, okay. When gamma decreases, your Cv and Cp values will increase, and that is what is causing this, okay. No more details than this, we will go to the next plot. I will go to some other plot and come back to this one. Now I am looking at M2 versus M1. I have also given U2 by U1 ratio in this dotted line. We will first look at M2 versus M1. What we are seeing is, as I increase my Mach number, my M2 drops. It drops steeply up to around Mach 3. After that, when I go to very high Mach number, say around Mach 6 and above, does not look like M2 changes much, it is almost a constant, okay. In fact, we can show asymptotic analysis will show you that it will go to some particular number. We will look at numbers, but I will do that next class, we will not do it now, okay. But I will look at U2 by U1 here, and again seeing that U2 by U1 is dropping and then becoming constant for hypersonic velocities, hypersonic Mach numbers. When we go very high Mach numbers, say above 7 or so, they are almost a constant. U2 by U1 is a constant, M2 is a constant for each of the gamma values, any gamma for that instant. Now we will look at details of what happens when gamma changes. If my M2, if my gamma is 1.67, my M2 is the highest. When my gamma decreases, that is my gas is more and more compressible, my Mach number drops, that is what we are seeing, okay. If my Mach number drops, my velocity decreases, my temperature increases, right, that is what decreases my Mach number, or you can think about it as R changes, but we will not worry about R change currently, we will have simple enough gas, okay. So if my gas is more and more compressible, I can go to lower Mach numbers, that is what we are seeing, okay. And here you will say that if my gas is more and more compressible, I will get even lower velocities compared to the previous velocity, that is what I will see here. Now we will go look at the next, this curve I have already seen, this one P02 by P01, the stagnation pressure drop, what I am seeing here is P02 by P01 is dropping very steeply for low Mach numbers, that is 1 to 4 or so, it is dropping very steeply. After that the ratio is going to somewhat constant, it is almost 0, but I will tell you, if I plot it in log scale, it will keep on dropping, it will never go to a steady state, it will never go to asymptote, it will keep on dropping, that will be the case here. Okay. And if I look at again gamma high value, it is having less drop, gamma low value it has more drop. Okay, this is again related to internal energy adjustment inside your gas, and because of that your entropy increases, which is equivalent to say that your P0 drops. Only one more plot, that is your delta S by R, which we just derived an expression for. If you look here, if my gas is more compressible, then I am having a condition where if my gas is more compressible, that is gamma is lesser, I am finding that delta S is higher. There is more internal energy rearrangement, because of which you are getting more entropy. I cannot prove this in this course, that is beyond this course. If you know molecular gas dynamics, we can talk about it. Currently you just assume that I am right, that is all. When the gas is more compressible, I will get higher entropy for the same Mach number. We looked at effects only based on Mach number as of now. Okay. Now the only thing left to do in this set of things is go and look at this M2, what is this asymptote value for a given gamma value. For a given gamma, it is one particular asymptotic value. We can look at that and we can show that P2 by P1 or T2 by T1 will not go to any asymptote. Those are the things we can show here. And what happens to this particular condition when m equal to 1? We will look at that also. What should be the value for P2 by P1 when m equal to 1? It just becomes 1. Okay. We should be able to get from our relations. We will look at all that this time. Okay. Next class at the beginning we will do that. We will hopefully remember all these plots, and we will just start with the equations next time. See you people next class.